Yes, thanks first of all for coming here today. My name is Moritz and I will talk about like two things that I really like and enjoy. And first we talk about graph databases, which is I think a very cool concept. And as you can maybe see from the title, we are talking about wine today. I already see some folks having already some wine, so good job. Yes, but how do we combine that? I will give you like a short introduction to it and then we go through it. Actually, this talk is together with our partner Neo4j. There's Alex, he's the guy from Neo4j. So if you have any questions about graph databases, about like all the stuff that is important about it, you can talk to Alex, you can talk to me, or to our other friend here. And of course with the Cloud Pilots together. Thanks for organizing all the stuff for us. So yeah. This is me, my name is Moritz, I'm working for the ATVANTAGE. We are a company based in Cologne and we are doing like everything around like all the new AI stuff. We are doing like a lot of analytics stuff and also like classical software development. I'm not originally from Cologne, I'm from Paderborn, but I'm currently living there. Yes, a colleague of mine actually created this slide. It's very charming because there's some picture where I still had hair. This is quite nice. And she also said that I'm an expert for machine learning and graph, and I wouldn't say that about myself all the time, but it's good if other people are saying this. So yeah, what do we want to do today? Actually, first I want to give you like a small problem definition that all of you get to know what we can do with recommender systems, and you will get in touch with it, and you even see that you are getting in touch with it day by day quite often. Then we have some example data set, which I will just shortly present to you since this is not the most important and interesting stuff. And then we will come to this interesting stuff. So see how can we like model some kind of recommender systems, and we can see how can we evaluate it. So pretty straightforward. Let's start. Problem definition. What is actually a recommender system? And you are getting in touch with the recommender system quite often day by day, because here you can see like my Netflix starting page. It's a tad bit old, but maybe some of your Netflix page is looking the same. And you are not anymore like searching for movies and series on Netflix. You are mostly seeing it and it's just generating you recommendations based on what you like, because the system knows what you like and it's pretty comfortable for you all to just like to know, okay, they are just like providing me some recommendations and I can just click through it and see, okay, I like this and I will watch a series. And this is not limited to Netflix. When we are taking a look at another point, this is Spotify. And actually, I'm a huge fan of hip-hop music, and Spotify always recommends me nice playlists. So it's pretty nice for me. It's an upgrade for their product. It's very, very good. And this stuff is not only limited to like digital goods, because you can also do it for physical goods. If you think about your favorite wine retailer and you're liking wine, and they are just like recommending you, based on data, of course, and not a sommelier sitting there and making a recommendation for everybody by itself. It would be nice, but of course it's not scalable and not possible. Why are we using recommender systems? I said it before, it's like a cool service and it like really improves the user experience. So when we're taking a look at studies, like 80% of the series and films that I watch on Netflix are based on their recommendations. So pretty heavy, or? Also it increases like strong customer loyalty. So if you have a good recommendation, of course people really like your service. They don't have to search for stuff, they are directly getting it, they are feeling happy. So they will not churn to another service. And of course, if they are not customers with you, they are highly you get a higher conversion rate. So people are more willing to pay for your service and even book your service, which is also quite cool. And in the end, all of this leads to, of course, to an increase of sales, and most of us works for business companies, and yeah, you know, we want to make money. That's what the business people want to do at the end, even if we are talking today more about like technical stuff. So we are also facing some problems. Cost and complexity, so we have often like a huge amount of data, we need to analyze it, we need to filter it. All the stuff I think the majority of you is doing day by day, and therefore the recommendation system of course is like an investment. You have to think about, we talk about like huge amount of data, stuff like this, you also need to be scalability and speed. So if you have big models and if you have like a lot of data, of course your computation costs are high and sometimes you need recommendations in seconds. So the user is hitting the website, maybe do something new and you want bam, a new recommendation. So you have to think about this one. Also, irrelevant recommendations are actually doing the opposite. So people are unhappy with your platform, they are not booking a service and they are more willing to churn. And last but not least, you have to think about biases, because trained models can be biased on some kind of influence. Like a colleague of mine, Lucas, gave me like a very nice example of it. Because I don't know if some of you also got hit by this bias thing by Spotify, but there was a song called Sarah, or Carpenter or something. Sarah Carpenter, I think. It's an artist, and she has a song called Espresso. And everybody got recommended by the song, even me. And I have never listened to her music or to the genre of her music before. And so it was fed with the blame. There's a good Watson article about it. You should read it. It's very funny. So now we know what are recommendation systems, why we should use them, what's actually problems with them. So, but we haven't talked about wines yet, and maybe we will see that in our data set, because we just found like a very, very cool data set. It's public available on GitHub. It's called X-Wines. And what is inside of it? X-Wines is a cool data set because we got like 3 versions of it, and we are talking about the full version. So we track everything because we think, yeah, more is always cooler, you know. And we got like 100,000 wines instances inside of this data set. So we have a database, we have 100,000 wines, and every of this wine has around 17 selected attributes. We will take a deeper look inside afterwards, but just imagine. We have 21 million ratings on the 5-star instances, so you can think about it like Amazon. 1 star is very bad, 5 stars, super cool. And we have about 1 million anonymized users. So for the users, we don't have any metadata, but for the wine we have. How does it look now? I forgot, that's actually a real data set from a real retailer. So this is not AI generated or stuff like this, so you can really see like behavior of customer inside of this data set, which is really cool, I think, because it makes more fun then, you know. So what information do we have about our wines? Of course, we have like a unique ID for every wine and a name for it. And then you can see we have some kind of variables. So we have, for example, the type of wine, like red wine, white wine. We have the elaborate of it, what grapes are inside of the wine. Actually, which meats are harmonizing with the wine, stuff like this. So a lot of categorical variables, and we also have some numerical variables like ABV, which means how many % of alcohol is inside of the wine. And we also got like a table overview for our user reviews. So you can see we have a unique ID for the user and for the rating and for the wine, and we can see, okay, which user rated which wine on the rating scale on which date. Pretty easy, understandable? Nice. So we are coming now to a recommendation system. We have now all this data and we want to use it, and we want to think about, okay, how could we now make great recommendations for our customers, because they have to bring some wines and we want to give them like great new wines which they like. And when we talk about recommendation systems, we actually distinguish between 2 different types. So we start with the left hand here with content-based filtering, and then we will go on with collaborative filtering. So content-based filtering is quite an easy approach and very straightforward. So we have a user here, for example, we can name him Bob. Like most of you who have maybe a background in computer science knows Bob at Alice, because it's always in all the lectures. And we have Bob, and Bob is a passionate wine drinker, so he likes some kind of wines and gives them a high rating. And the idea is now, Bob hasn't drink all the wines we have in our shop. So we want to recommend to him similar wines to the one Bob already likes. Sounds good, or? A good idea? So how can we do that? When we talk about similarities, we know we have to do some math, statistics, stuff like this. And it's pretty hard to do statistics or mathematics with strings or with text. That's not possible, so we can't calculate with it. So what do we want to do? Actually, we want to create like a numerical representation of all our features, which we have for a wine, to characterize this wine in some kind of way. And what we are doing, or what I try to transform, is we are trying to build like an embedding. And an embedding is just like a vector from the guys who have maybe a background in math. You can just think about it as a list of numbers. And you can store different numbers, and these numbers, of course, should characterize in some kind of way your wine. And you have a different number of numbers. So the entrance you see here, and this is called a dimension of a vector. So the number of numbers I have inside is the dimension. Why do we want to do that now? Because vectors have like very, very cool attributes that you can calculate similarities between vectors. And you can use like the cosine similarity. So cosine similarity calculates cosine between the angles of a vector. And we can see here like an easy approach when we have a 2-dimensional vector that's good to represent, it's easy to show. And we see that we have an angle of 60 degree, and we can use the cosine there and get a cosine similarity of 0.5. And what's the idea behind it? The idea is that we measure how strongly 2 vectors point in the same direction. And we can assume if vectors are directly pointing in the same direction, they are pretty similar. And also we can say, okay, if we find a good numerical representation for our wines, when they are similar and also their vectors are similar, we are getting like a good similarity. Okay, but how we do with that now? And we will start like with some classical approach. That's why it's called maybe classical versus graph approaches. And then we will come to the graph approach, okay? So by classical approaches, you can do like, or directly calculate your embeddings based on your features. And we distinguish here between numerical values and categorical values. So we want to create a vector like this for our first wine, and we can say, okay, we have a numerical value ABV, so the alcohol which is inside of the wine, and we can use some kind of min-max scaling because we want to bring them on a scale from 0 to 1, and we are just using the formula here, so we are using the value minus the minimum value of all the ABVs you have in your data set, divided by the maximum value of all of the ABVs minus the minimum value. We can assume we have some alcohol-free wines because alcohol-free wine is quite a huge business, so we can ignore the minimum then. And we can assume maybe that 12 is the highest here, so we can calculate for our first wine the first entrance in our embedding. We can also do that for category variables, and there we have different kind of approaches. So we use one-hot encoding, where we say every characteristic that is inside of the type is represented by one number. So the first number means if it's a sparkling wine, the second number means if it's a red wine. Of course, we have more in our whole data set, but to keep it simple and easy, we can just assume that we only have the 2 ones. And this is how we get like to the second and third entrance of the vector. And we can do something called target encoding, where we have like a list of number. So if you're taking a look at the vintages, you have like a list of number, and you can, for example, average them. And of course, you're getting like values, and we're getting like our last entrance in the vector. And the smart people see these two are not equivalent because we are again doing min-max scaling with these values. So this is like a classical approach. Guys who come from machine learning maybe knows this a lot because back in the days we did like a lot of this stuff. But we have also different approaches. So a second maybe more classical approach, and we are going more also in the way of machine learning, is to use text embeddings. And most of you who are maybe working with some kind of large language models, with RAG, with all this stuff, already know what text embeddings are, but we can just like easily explain it here. So we are changing the kind of representation of our features. So we are not thinking about like the data in the table anymore, but we are creating texts out of it. So we are just like concatenating like all the stuff you have here, so all of your features. So you are writing type equals sparkling, elaborate equals rarity 100%, and so on for all of your wines. And you store it in some kind of string. So you just have a text for all of your wines, and now you want to use this one to create embeddings. And what you can do is, you can use, you can do it based on sentence transformer. And sentence transformer are like pre-trained neural networks for semantically meaningful embeddings. What does that mean? Actually, you are assuming that you train it like on a very, very large database. And these pre-trained neural networks can generate like meaningful embeddings. So your embeddings are based on the content which is inside of the text. And if we have similar contents inside of the text, we are getting similar embeddings. And if we are again calculating like the similarity, we will get a high similarity. And the idea is, of course, if the features are pretty similar, also your text is pretty similar. So your vector is pretty similar, so the similarity calculation works in a good way. We can make here an example. So we are taking like here all of our text. We are passing it to a sentence transformer. This is SBERT. This is like quite a famous framework for it. You can use a different kind of models. So there's not only one sentence transformer, but there are a lot of. And you're getting an embedding. Actually, the dimension of this embedding depends on the model you're using. And you are seeing like these values. And the stuff with this values, or the features inside of this embeddings, is that these numbers are looking quite random for human beings. So it's very, very hard to interpret these numbers here by a human being, because we don't know what actually the first column means or what the second column means. And that's why we call features like this latent features, because a model can interpret it and it makes sense in some kind of modeling, but it's hard for humans to understand what's actually inside of the values. So we talked like a lot about the classical stuff, and I said, yeah, graphs are super cool. So how do we come now from a data structure like this? So we are talking about like table data structure or relational data structure to a graph. In a graph, we store the data in some kind of different concepts. So we are not using like tables and linking the tables anymore. We are storing data inside of nodes and relationships. So these edges between these nodes. And how do we model that? Actually, we give every node a label. So we have like a lot of nodes for the wines, and all of the wines have labels on it. And you can directly store, of course, properties on these wines. And in our case, we are just storing the numerical properties on our wine node. So you can imagine we have like a lot of wine nodes, and we are storing like the ABV value, which I think is the only numerical value, directly on the wine. And for the rest of the characteristics, we are also creating nodes. So for all the dishes which are in our data set, we are creating like nodes. For all the regions which are in our data set, we are creating nodes, and so on. And we start linking our wines to the dishes or to the regions which are like associated to them. So when you take a look at the data set, all of your dishes which stand like in the feature of your dish, you are creating like a connection between them. And you can also give like labels here for the edges, and you can also write like properties on these edges, because if you want to use now not only creating like this based on the wine data, but we would also want to include the ratings inside of the graph, we will create for every user a node, and then creating edges between every user who has rated a wine, giving it this rated label, and directly plugging like the, I don't know how it's called, number of rating or the height of the rating directly on this edge. So you can imagine now we have like a graph with like a nice graph structure and like a lot of nodes, but how do we go on now? And the thing we are using here is like we are using an algorithm called fast random projection. And this is an algorithm which is directly inside of Neo4j. So you have their libraries called GDS, so Graph Data Science, and you can directly use this algorithm inside of it. And what this algorithm is doing? The algorithm is actually creating or calculating embeddings for one node or for multiple nodes. So we can, for example, calculate embeddings for all of our wine nodes now. And how do we do that? Actually, you do that based on the structure of the graph. We will have an example later, which maybe shows you more how we use the structure, but you can think about it. You have like now a very, very huge graph. So a lot of connections, a lot of nodes. And you want to push all of this inside of embeddings. So you are actually making a massive dimension reduction. But when we talk about structure, what are things which are influencing the structure? And for this, I just put here on some kind of documentation, which is from the GDS of Neo4j. And here you can see what you can actually configure here. So you can on one hand configure what kind of node labels should be added to my projection, or so to my graph structure. What kind of relationship types should be inside of it. So I can say, of course, I can take everything, but I only can take like some of the nodes I want to have. You can, for example, also include what kind of feature properties. So features which are on the nodes should influence my structure. And of course, you can use like what kind of relationship properties should be influence my structure, okay? So you have like a lot of configuration parameters, also some more, but I didn't want to go through all of them because it's a tad bit boring. So you now see, okay, I can influence what actually giving me the structure of the graph. And this is a tad bit abstract. That's why I maybe should give you like an example here, and we can see in a high level way how the algorithm is working. So you're thinking about, you're seeing here we have two wines, and we have like, of course, the ABV written on it, you can't see it here, and we have like all the attributes of the wine. So for example, if it's a red wine, or on how many degrees you should drink it, stuff like this. So we have built a graph, and we put all of our nodes now inside of our graph projection. And now we want to create like embeddings for this and this node. And you see, they are sharing like a lot of nodes. So the idea is they're sharing a lot of nodes, they're pretty similar. You can also see we added here an edge at the end. This is similar. And how does this go? And actually, this is done by a linear projection of all of these nodes. So you are randomly assigning like embeddings to every one of these nodes. So all of these nodes have now an embedding. It's randomly generated. And now you are making a linear projection out of all these embeddings which are linked to your node. So you can think about it, this node is influenced by all these nodes. And the linear projection means something like averaging all the vectors. So all the embeddings together, and then you have got your embedding for this node. So you can think about it, if you have like many links, these are pretty similar, because the nodes which are influencing the embedding are also pretty similar. We can see another example, and then maybe it's getting clearer. We are seeing again two wines. This is a white wine, this is a wet wine, and they are not sharing that many features. So they are not very similar. They don't have a lot of common nodes. So in this case also, the embedding at the end is influenced by all of these nodes, and you're just sharing two. So of course your embedding will get very more unsimilar. So now we find similarities for our wines. So we can see here, for example, some wines. but this similarity of course is not random. In all of our approaches that we saw, we want to do it on the features we have for, or the characteristics of the wine. But we also want to include something, if we're thinking back about the idea of content-based filtering, is that we say, okay, not only the similarities to the wines I as a user already have drunk should be influenced, like the recommendation score, so what gets recommended to me, but also the rating that I give to a wine. But when you think about it, I have like a wine and I think, oh, it's medium good, and I have a wine which I said is really nice. This should also influence the recommendation score. And we just created here an example formula how you can do that. So you can take for each of the wines which you haven't drunk, you can calculate the recommendation score by, for example, 0.5 times the wine similarity, which you have here, plus 0.5 the rating you assigned to the wine you already drunk. Of course, you should, in a real world scenario, you would do that with some kind of business guy or something who knows like the rules, who knows maybe how the user behaves and stuff like this. But we can see here in our example, this wine is like very good rated by my user, this wine is okay rated by my user, this is not very good rated by my user, and you can see here how big the edges are, actually represents a higher number, that this wine has like a lot of very similar wines, and this one has like a lot of wines which are not that similar. So you didn't find many similar wines to this one. So you're calculating the scores, and you see that these scores are even higher. So all the gray edges here are the recommendation scores. So based on this image, you would recommend like these wines in some kind of order. Okay? Very nice. So now we have talked about like the lonely approach if you're using content-based filtering because you are just doing it on your data. But what would it be if you are doing it also based on other users? And the idea behind that is collaborative filtering. We can again maybe make an example and then you will see. So here we have Bob and finally also Alice joins. And we have our user Bob again, and I'm the user Bob, and I'm like a certain kind of wine. And now another user is coming, and she's called Alice. And she also likes similar wines to mine. So she has the same taste actually as I have. But she has drank way more wines than me. So the chance that I like the wines that she also likes, and I haven't drunk it, and so that I get recommended is that I also like the recommendation. So I'm using like a similar user, I find somebody who has a similar taste, and you can think about it like asking him, okay, what would you recommend to me? And that is the idea of content-based, collaborative filtering. How did we do that now in a classical approach? And we can use singular value decomposition for it. It sounds like very confusing, and you first see like a matrix and thinking, okay, we are doing a lot of math. I will explain it on a higher level. Because this algorithm is part of like the Netflix price algorithm. This was a famous price for recommendation systems by Netflix. Of course, in the Netflix implementation, it's way more stuff inside of it, but the main idea behind this is something like this. So we are now representing our users and our wine in some kind of matrix. And we have like here all of our users. So every row is the user, and every row is the wine, and every column is the user. And we can see, okay, user 1 rated the wine 1 with a score of 4, and rated the wine 2 with a score of 2. And actually this question mark means we have no rating for it. Now if you think about this matrix, it looks quite okay, but now think about the real matrix. So you have 1 million users and 100,000 wines. It's a huge matrix. And of course not all the users have drank like 100,000 wines because you can't survive that. That's impossible. Most of them have maybe drink 10 or 20 or something. So you have like a matrix that is very sparse. So like a lot of values are missing. And the idea behind is now to predict these values. So we are predicting it and seeing, okay, for what wine the user hasn't drunk yet, do we get the highest predicted score between 1 and 5? But how do we do now the prediction of it? And we are using a trick which is called matrix factorization. So the guys who have been in algebra, like my friend here, knows this stuff. So you can actually represent every matrix as a multiplication of other matrices. And we are creating like here a matrix U and a matrix W, and this is transposed, thank you. I always bring it back into my head. And we are creating like 2 new matrices. But what does user represent? This is just some kind of formula. We want to get recommendations. And the idea behind this is that we are creating one matrix U, which represents the users in some kind of way, and one matrix W, which represents like the wines. And we added here like 2 dimensions of features for every user and for every wine. Of course, in the real world scenario, it would be bigger, but to keep it simple and easier, we are just creating here like 2 features for every user. And now we have to think about how could we now see if our features are working good, so if they are predicting our values good. And the idea behind this is to use like the already rated wines. So this is the actual rating given by the user. We have it for some kind of wines, and the idea behind this, how could we see that we are getting a good prediction? And the idea is that the difference between like the actual value of the user and the predicted value should be like very low, because then you are getting like realistic predictions. Makes sense, or? But how do we get this now? And actually we can calculate like for all of these. So we can of course first like generate 2 random vectors, and we can then predict like this value and so on, and can see the difference between all of them. And now we want to improve our features, so to make it better, to get the prediction nearer to what is actually done. And for this we used an algorithm called stochastic gradient descent. This is just like minimizing in like a lot of iterations, adjusting these values here in the features to minimize the difference between like these actual values and the predicted values. And after like a lot of iterations we are finished, because we can't improve our features anymore and we have like the best state we could get. And then we can go on and use these matrices to actually calculate the missing values. And you see here, for example, for user 1, I have a score from 4.1 for wine 3 and 3.7 for wine 4. So I would first recommend like wine 3 and then wine 4 and so on. You can think about this like in a very bigger dimension. Of course, you will get like a lot of different like predicted ratings for every user. This is quite cool, but we can also do it with graphs again. And when we talk about doing this in graphs, we have to remember what we have done before. So you all can maybe remember how we create like the embeddings for the wine nodes. So we are just like saying, okay, if we are sharing like a lot of nodes, we are creating embeddings for the wine, and they are just like in some kind of way have the characteristics of the wine inside of it. And now we are not only doing just one hoop, so we are doing 2 hoops. And that means we're first calculating like the embeddings for the wine. So we are using the features and we are getting like good representations of the wines. And then we are using the embeddings of the wine and again doing like a linear projection with all of these embeddings. So we are again averaging these ones and creating an embedding for the user. So we have like the characteristics of all the wines the user has drunk inside of my user behavior now. And we are doing this because similar taste is more than just liking the same wine. Because some people maybe have never drunk the same wine but have a pretty similar taste. So we are first like averaging over the characteristics and then averaging over the wines. And you can see this here in the example. So we have here, for example, my user, and I want to find like a recommendation for him. And he rated this wine quite well. Oh, Jesus. And we can see that these 2 wines are pretty similar because they share like a lot of notes. And this user has rated this wine quite well. So these 2 users are similar because they are liking the same wine. Makes sense, huh? So I would definitely recommend this wine to this user. But again, how do we calculate this stuff now? Because we not only want to include how similar the users are, we also want to include how good the similar user actually rated the wine. Because if a person who has a similar taste than me drinks the wine and says that this is quite a shitty wine, I don't want to drink it. Okay, so again we have to find some kind of recommendation score, some kind of formula. We've given you that example again, so we can again like maybe averaging it in some kind of way, and using 0.5 times the user similarity score plus 0 times 0.5 times the assigned rating. And at the end we can create like a recommendation engine for all the stuff. But we have now different approaches, and of course if we have different approaches we need some kind of evaluation for it. So we need to check what is the best approach. And we have different matrices for this. So we have a predictive quality matrix which measures the relevance of the recommendations. This is done with precision, recall and F1 score at K. We have ranking quality matrices, so we see how good your ranking is actually. And of course we have business matrices. So let's maybe take a short look. I still have time left? No, it's okay. Sorry. For example, we can get the precision at K, so how many of the relevant items. So here's an example, we have 20 items. And one of the users said, these items are relevant for me, these red items are not relevant for me. So the pink ones are relevant for the user, and the gray ones are not relevant for the user. And we can calculate, for example, precision at K by taking all the relevance items until K. So we have 5, because we have 5 of these pink ones. And of course we have K of 10, so the precision at 10 would be 5 divided by 10, 0.5, okay? We can also do that for the recall. Here we are searching for all the relevant items we are finding at k, so at 10 we are again finding 5 items, and we are dividing it by all the items which are relevant. So in our case, here are 3, can't see that good. Actually, we have 8 relevant items of all of the items the user had rated. So we have here a score of 0.625. And of course, we can just combine the score using the F1 score, like a lot of people who are maybe doing machine learning with classifications already know this scores, by just using this formula. And then you're combining it and try to middle it in some kind of way. We can also talk about ranking quality matrices. So the mean reciprocal rank actually measures when the first relevant items appears. So you have a list of items again that users say, these are relevant for me, these are not relevant for me. And when your first relevant item that you are predicting should be recommended to the user, then you get a reciprocal score. So in our case, the second item is the first one which is relevant. So you are dividing 1 by 2 and getting 0.5. If you would hit it at the fourth item, of course we would divide 1 by 4 and get a score of 0.25. And we can also use the hit rate. So this is actually, here you have like the data sets for all the users, where they say, okay, this is relevant for me, this is not relevant for me. And you can just measure hit rate at 3. So in the first 3 items, do I hit at least 1 relevant item? And here we see for 2 users, we are doing good. And for the third user, we are not doing good. So we are hitting the rate for 2 out of 3 users, which then calculates the score. And business matrices, actually I'm not a business guy, but I can also think about it. So what is the increase of revenue gaining by my recommender systems by testing maybe if I don't use it and if I use it? What is the click-through rate? So how often actually does a user click on the displayed recommendations, and how often recommendations are actually leading to a buy? So also pretty straightforward. That's from like the perspective of my talk. I just have to make some advertisement. On the 6th of November is like a very, very cool online conference from our friends from Neo4j. It's called Notes. It's totally free. You have like different time slots for different time zones. So it's like 24 hours conference. We have like, they have like a lot of good talks. And it's online, and it's majorly like about all the stuff you can do with graphs, from GraphRec to graph machine learning, everything about like a lot of AI topics. You have like a lot of good speakers. Also, I am here. Hello. Yes. If you want to join, just Google for Notes or scan this QR code, and you will find it. And I hope a lot of you will attend there. Actually, my presentation is not that good for you anymore because I will take a similar one to the one today. Okay, but thanks for listening. If you have any questions, feel free.